In this video, we are going to be looking at how a material responds to forces. Now, when you compress or you stretch a material, what happens? It deforms, right? So, we want to study that deformation that occurs in a material. And the material that we're going to be using is called composite materials. So, we are going to be looking at linear elastic stress strain relationship, linear elastic stress strain relationship, right? So like I said, that the material that we're going to be using is called composite materials. What are composite materials? Composite materials, it is formed from at least two distinct materials, of which one is the fiber and the other matrix. So a composite material is a material that is made up of two or more distinct materials, where one of the material inside that composite material is called a fiber and the other one is called a matrix. So what's the difference between a fiber and matrix? So what's the meaning of fiber and matrix? So a fiber, it acts as a reinforcement. It also provides strength and stiffness. So a fiber provides strength and stiffness. Then the second one is matrix. What is a matrix? A matrix, it serves as a binding agent. Matrix serves as a binding agent for the fiber. So every composite material is made up of two distinct materials, two or more distinct materials, a fiber and a matrix. The fiber serves as a reinforcement. It provides strength to the material and stiffness, while the matrix just binds the fibers together, holds them together. That's the meaning of fiber and matrix. So in this course, we're going to be exploring composite materials. We want to understand when you apply force to the material, how will it deform? How will this composite material deform? That's what we are going to study. So a typical example of fiber and matrix is simply fiberglass. So a composite material, an example of a composite material is called fiberglass. Now, a fiberglass, that's example that we are taking, e.g., is made up of two other materials. Inside this fiberglass, we have glass fibers and we also have something we call resin. So this glass fiber serves as my fiber and this resin is now my matrix. So this is what you should note, that an example of a composite material is fiberglass, and inside this fiberglass we have two other materials, which is what? Glass fiber and resin. The glass fiber serves as my fiber. What does the fiber do? It provides strength and stiffness to the material. While this resin is the matrix, it binds the fibers together. So that is what we talk about. Anytime we are mentioning anything concerning composite material, this is what we are referring to. Okay, so after we've understood we've understood what composite material is, the examples of composite material. Now let's look at mathematical tools or concepts that we use to predict how a material will deform when you apply force. Remember, that's the objective of this topic or the course. We want to understand when you apply a force to a material. Take for instance, you have a rod in a block, this steel rod in a block. The block is serving as my matrix, while the steel rod is the fiber. So we want to understand when you apply force to the material, how will it deform? So for us to be able to predict that deformation, we need some mathematical tools or concepts that will be able to help us to do that. So the first mathematical tool is called coordinate system. So they are special coordinate system. For us to be able to describe this deformation, for us to be able to predict this deformation, we need to make use of special coordinate system. The special coordinate system we use in this topic is called principal material coordinate system. You can either call it principal material coordinate system or you can call it local coordinate system. They mean the same thing. So what are principal material coordinate systems? Principal material coordinate systems are simply a set of directions or axes that are used to describe the properties of a material. They are set of directions that specifically we are talking about. Principal material coordinate systems are set of directions, or you can call it axes, that are used to describe the property of a material. So remember, if you don't want to call it principal material coordinate system, you can call it local coordinate system. They mean the same thing. So they are used to predict help us to describe the properties of any material. So that's coordinate system. Now let's consider a layer of a composite material. The layer of a composite material, a single layer of a composite material is called a lamina. So take for instance, you have something like this. Let's consider a lamina. Now, what did I say lamina is? A lamina is a single layer, a single flat layer of a composite material. You have something like this. Okay, so we want to consider a lamina. This is the lamina. Now every layer of a composite material has three coordinates. That's actually the principal material coordinate system. It's like this. You have, let me use a different marker for that. Okay, so every principal material coordinate system, every lamina rather, has three coordinate systems, three directions. All of them have three directions in this course. So the one direction is dominated by fiber. Remember we said at the beginning of this video that every composite material is made up of what and what? Fiber and matrix. So this lamina, a layer of the composite material, is also made up of two materials, like fiber and matrix. So my one direction is always dominated by fiber, while my 2 and 3, they are dominated by matrix. Okay, so now we know the principal material coordinate system, which is 1, 2, and 3 directions. Let's look at the meaning of each of these directions one after the other. So starting from the first one, you have for number 1, for one direction. Now one direction we normally use for an easy way to remember it is that we put an L here for one direction. What does this simply mean? It simply means that one direction is the longitudinal direction because of this L. So one direction is the longitudinal direction, and this direction is aligned with the fiber, just like what we said here, dominated by fiber. So our one direction is longitudinal direction. It is also aligned with the fiber, and it is aligned with the fiber, and it's usually the strongest and the stiffest direction. So we need to know that every time you hear the word one direction, it is the longitudinal direction 1, it is aligned with the fiber 2, and it is always the strongest and stiffest direction. Now the second one is called the 2 direction, which is what you are seeing here. Now the 2 direction, we put a T here. What does it mean? So everywhere you hear 2 direction, it is a transverse direction. The 2 direction is perpendicular to the fiber direction. So 1, it is the fiber direction. Sorry, it is the transverse direction. Another one is that it is perpendicular. It is perpendicular to the fiber direction. So these 2 directions is perpendicular to the fiber direction in the layer of the lamina. So in the plane of the lamina. So this is perpendicular to the fiber direction 2. Now the last one is the 3 direction. The 3 direction is what you are seeing here. The 3 direction is denoted as Z. We use Z to remember what it means. Now, the 3 direction is the thickness direction. That's just what you need to know. Anytime you are referring to thickness in a material, this height, it is the thickness or the 3 direction, which is the thickness direction. So in everything that we are doing, every calculation we are doing in this topic, we are going to make reference to these 3 directions. All the calculations are based on these 3, are done on these 3 directions. That is because it was principal material coordinate system or local coordinate system, or you can even still call it 1, 2, and 3 coordinate systems. So that's what we need to know. So this is the first mathematical tool or concept we need to know for us to be able to predict how a material deforms. Let's look at the second one. So the second one is stress and strain. Stress and strain. Now, in this course, we make use of stress and strain. We want to understand how many stresses and strain actually act on this composite material. So let's start with stress. So for stress, we know that mathematically, stress is what? Force, ratio of force over area, force per unit area. Alright. Now this stress is broken down into 2. We have normal stress, normal stress. What is normal stress? We know that normal stress, it is denoted by sigma. So anywhere you see something like this, we know it's normal stress. Now in this course, remember that all the calculation we are doing is based on these 3 coordinates. So our normal stress, it is sigma 1, sigma 2, and sigma 3. Why? Because it's based on these 3 coordinate systems. So sigma 1, 2, and 3 is our normal stress. Now you can define normal stress as stress, or you can say that it acts perpendicular to a surface. So anywhere you see any force or stress acting perpendicular to its surface, it is normal stress. that we are referring to, and it is either tension or compression. So a normal stress can either be tensile or compressive. So if it is tensile, if it is a tensile stress, if it is a tensile stress, we use plus while writing the stress. Why if it is compressive, we use minus. So please take note, very important. Whenever you are dealing with a tensile force, in the question you'll be given that this is a tensile force. So if the force is tensile, I will denote it with a plus. As I'm writing what it is, I'm going to attach a plus. And when it is compressive, I'm going to use a minus. So that is for normal stress. And because we have three coordinate systems, our normal stresses will be acting in these three coordinate systems. So the second one is, let's use II under stress. So the second one is shear stress. Shear stress. Now shear stress is denoted by tau. So now, unlike our normal stress that we have normal stress in one direction, normal stress sigma 1, sigma 2, sigma 3, for shear stress it is actually acting in between two planes. So our shear stress, remember, for something to shear, there must be two surfaces or two planes acting opposite each other, then shearing can happen. So it is not independent on, it's not just one coordinate like this normal stress. It is depending on two plane or two surfaces for it to be able to share. So our shear stress is always like this. Remember, we are dealing with these three coordinates. So we try to write the combination of the three of them, picking two at once. So you have shear stress 2, 3, 1, 3, and tau 1, 2. So that's the only combination that you can get out of these three coordinate systems. Remember, for shear stress, we are talking about shearing. So it's not like our normal stress that is just acting on each of these coordinates. No, it needs two surfaces, two planes for it to share. So that's why we have 2, 3 here and here. We have 1, 3 here and here, in between 1 and 3. And finally, we have tau 1, 2 in between 1 and 2. So that is all for normal stress. Now, that's all for stress. Now let's go to the second one. The second one is strain. Now what about strain? So for strain, we know that strain is the deformation caused by the stress. So the definition is that strain is any deformation caused by stress is strain, and it is broken down into two. We have our normal strain, just like how we have normal stress, we have normal strain. What is normal strain? Normal strain is the ratio of the change in length to the original length. So mathematically, we know that normal strain is, first of all, it is denoted by epsilon. So same way, the way we have normal stress acting in each coordinate, we also have normal strain acting independent on each coordinate. So we have epsilon 1, epsilon 2, and epsilon 3, and mathematically it is what? The change in length over what? The original length. That is everything you need to know about normal strain. Then let's go to shear strain. Now for shear strain, it is different. Just like how we have our shear stress, remember, for shearing to happen we need two planes. So for shear strain, it is denoted by gamma. So the same way we did for shear stress is the same way we are going to apply shear strain. So it's going to be in between two planes. We have gamma 2, 3, gamma 1, 2, 1, 3, and gamma 1, 2. Exactly what you have here. That's what we have here. So that's for shear strain. So another important mathematical concept we need to understand is shear and stress and strain. It helps us to predict how materials deform. So we are going to go to the third one. The reason why we did this second one is because we need to find a relationship between stress and strain. For the third one, that's relationship between stress and strain. Okay, so to be able to describe how a material deforms, we need two main equations. For us to be able to describe how materials deform. The first equation under this number 3, the first equation is called it's called compliance matrix. So it's called compliance matrix, and it is like this, an S. Please take note, very important. Compliance matrix is not having a C on it. For compliance matrix, we are going to use S, capital letter S, to denote it. So compliance matrix is just trying to tell us how a material will deform when you apply a given force to that material. So the equation is like this. You have something like this. Epsilon equal to the compliance matrix S times stress. So this is it. Now let's write what each of these stands for. For this first guy, this is simply the column. It is the column strain vector. This is the column strain vector. Column strain vector. Now remember, this is a vector form. In a vector form, a compressed form, I can choose to rewrite it, express it in full. It's going to look like this. So this is simply, if I want to write everything out, I'll have something like this. Now look at your second mathematical concept that we talked about. What's that? Or strain. How many strain do we have? Two. Normal strain and shear strain. And each of them are three column here. So that's what it means. So this place is my strain. I have to write the two classes of strain that we have on the board. So that will be what? Epsilon 1, epsilon 2, epsilon 3, gamma 2 3, gamma 1 3, and gamma 1 2. So this is for strain. So anytime in this topic that we are referring to strain and we write it in this format, it's simply everything that you are saying here written in full. So that is what strain stands for. And let's go to stress, the second one. So for stress, it stands for column. This one that you're seeing here stands for column stress vector, right? Now, if I want to write it in full, what I will simply do is just similar with what you did here. So what am I going to do? Good. We're going to write it. Remember, we said here that our stress is broken into two, normal and shear stress. So if I break this one down, if I want to write everything that it has, it's simply what? Sigma 1. Look at what you have there on the board. Sigma 1, sigma 2, sigma 3. What else? Tau 2 3, tau 1 3, and tau 1 2. Do you get the point? So we have written what this one stands for in the full. We have written what this one stands for. This is the main guy, this S. So for S is our compliance matrix, like I've said before, compliance matrix. Now, this S comprises of three material constants. We used to call it material constant. You can still call it elastic constant. So S comprises of three elastic constants. What are they? Number one is called the Young modulus. We use capital letter E to write that, Young modulus. Number two is the Poisson ratio. Poisson ratio. So Poisson ratio, we use a small v to represent it. Then the third one is the last one. It is shear modulus. So we use capital letter G to represent it. So in this our compliance matrix, we're dealing with three material or elastic constants, and these are the three material constants. And my compliance matrix is a 6x6 matrix. Let me show you what it means. So if I want to write the same way we have broken this, our strain and our stress vector, we're writing it in full. Let's write what this S is in full. Remember, it's a 6x6 matrix. So it's going to look like this. So our S is going to be in full form. You have S11, S12, S13, 0, 0, 0, S21, S22, S23, 0, 0, 0, S31, S32, S33, 0, 0, 0, 0, 0, 0, S44, 0, 0, 0, 0, 0, 0, S55, 0, then finally 0, 0, 0, 0, 0, S66. So this is a 6x6 matrix. Now I will explain why we have zeros in this matrix later on. Okay, so this is how our compliance matrix is in full. Now, what does each of these elements mean? What are their formula? Let's write them down. Now, whenever you have something like this, remember I and J, it simply means, for example, when you have S11, my I is 1, my J is what? Also 1. Same thing applies there. I and J means wherever I have 1, that's my I. J is what? 2. What about here? I is 1, J is what? 3, and so on. So whenever my I and J are equal, the formula for this Sij is going to be 1 divided by Ei. So whenever also my I is not equal to J, the formula is going to be minus Vji divided by Ej. Do you get the point? So what we are just trying to say, let's go back to our matrix. Now let's start from S11. S11, the I and J, are they equal? Yes, because I is 1 and J is also 1. So whenever they are equal, what's my formula there? 1 over E1. Simple. Let's move to the second one. S12. Now, is I and J equal here? No, they are not equal. Because they are not equal, what's my formula? Minus B. Now in this place, where's my J? This is I, this is J. Can use a different marker to write that. I have I have J. Right. Good. So we have S12 now. So remember, they are not equal. Because they are not equal, I'm going to use this formula. So we're writing it to be what? Minus B, J is what? 2. So it will be minus B21 over what? E, what's the J? 2. So that's how we do it for each of the elements here. So let me rewrite it now that we have gotten a hang of it. But each of them mean. The only exception to this rule is everything that is not here. Now this S11 to S33 belongs to this rule, but S44, S55 and S66 they are unique. So for S44 our formula is actually 1 over G23. For S55 it is what? 1 over G13. For S66 is what? 1 over G12. Now if you observe 2, 3, 1, 3 and 1, 2 still comes from what we said initially, that anytime you are dealing with a sharing, we need two planes, two coordinate systems, right? So that is why you are still making use of 2, 3, 1, 3 and 1, 2. You get my point? So remember this is called share modulus G. So therefore we need two surfaces for it to share, unlike the other guys. Okay, so let's rewrite it now. So my new S, that's my compliance matrix now. I want to put the formulas that we have written. So S11 will be what? 1 over E1. Then we have S12 will be what? Minus D21 over what? E2. S13 will be what? Minus D31 over E3. The remaining are 0. So 0, 0, 0. So S21 minus D12 over E1. Let me quickly write it. 0. Okay, so we have written what each of these stands for, right? So let's go to, remember we said that our relationship between stress and strain, for us to describe that deformation, we need two equations. We've taken the first one called compliance matrix. We've looked at each of the formulas, what it means. Now let's go to the second equation. The second equation is called stiffness matrix. So let's do that. For the second equation, that's B, stiffness matrix. Now stiffness matrix is denoted by C. Now you see the funny thing about the denotation. If you look at compliance matrix, we are denoting it by S. While for stiffness matrix, we are denoting it by what? C. Whereas in our understanding, it would have been much easier if this compliance matrix has a C because of the compliance at the beginning. The C at the beginning. While for stiffness, it would have been better if our stiffness matrix have an S there. But it's the other way around. So I'm pointing out areas that students can easily make mistakes. So anytime you have stiffness matrix, it is C. While compliance matrix, it is S. Okay, so the stiffness matrix is the inverse of the compliance matrix. What does it mean? So this way that I have my stiffness matrix C, it is simply the inverse of S, which is this S inverse. So what's my compliance matrix equation? That's the equation. There we have the epsilon is equal to what? The compliance matrix times what? The stress, right? So remember it's the inverse. So let's make this one subject of formula. If you make this subject of formula, what do you have? The stress is equal to what? My 1 over S times epsilon. If you make this one standalone, this one will divide this epsilon, right? Now, what is 1 over S? 1 over compliance matrix. See it here. It is stiffness matrix because stiffness matrix is the inverse of my compliance matrix. So my new equation is going to look like this. This is equal to, this has been replaced with C, right? Then I have my strain epsilon there. Now if I want to write this in full, we already know what each of these elements stand for, right? Let me rewrite it in full. Let's start from this one. So for this stress, if I rewrite it in full, what is it going to look like? We've done it here. So we start with our normal stress, that's sigma 1, sigma 2, sigma 3. After normal, we follow it with what? Shear stress. So that will be what? Tau 2, 3, tau 1, 3, tau 1, 2. Now whenever we are the order of this numbering, 2, 3, 1, 3 and 1, 2, it has to correspond with the order number from the epsilon. So even if you choose to start with 1, 2, 1, 3, 2, 3, make sure that whenever you're writing for the epsilon, it has to correspond. Same thing when you are going to write for, just make sure that both sides correspond with whatever numbering you choose. So for me, I prefer sticking with 2, 3, 1, 3 and 1, 2. It's easier to remember. So I know that when I'm writing the other side, it's going to correspond. I have to write the same thing. Okay, so that is for our stress. Then what about for this stiffness matrix? It's still similar. I'll have C11, C12, C13, 0, 0, 0, C21, C22, C23, 0, 0, 0, C31, 32, 33, Abby, 0, 0, 0. You have 0, 0, 0, C44, 0, 0, 0, 0, 0, 0, C55, 0, then 0, 0, 0, 0, 0, C66. So this is the final matrix for the stiffness matrix. Now let's go to this epsilon. You already know what it's going to look like. It's going to look like exactly what you have here. So it is what? You start with the normal one, the normal string. Epsilon 1, epsilon 2, epsilon 3, right? Followed by what? The shear string. That is what? Gamma 2, 3, 1, 3, and 1, 2. And like I told you, whenever you're numbering, especially these 2, 3, 1, 3, and 1, whatever order you choose to start with, make sure it corresponds with what you have here at your right hand side. Okay, so we have looked at the third mathematical tool and concept that we use to predict when a material is deforming. Let's look at the final one. The final one is called Reciprocity Relation. So let's quickly look at that. So the fourth one is called Reciprocity Relationship. Now, what thing you need to understand is that is not all the materials are not actually independent. All the constants are not independent. Some are actually connected by a special rule. What is that special rule? That's what we are going to find out. So reciprocity relation is that saying that all these material constants, most of them are not independent, they are not standing alone. They have a special relationship that linking both of them together. So what's the first relationship? When you have V12 over E1, it is similar with where you have V21 over E2. They are symmetric. So that's for the first one. When you have V31 over E3, it's similar with when you have V13 over E1. And also when you have V23 over E2 is similar with where you have, remember this V, our Poisson ratio, is actually a small v. Do you get me? So it's not like velocity, it's a small v. So V23 over E2 is equal to V32 over E3. So these three reciprocity relation is very important in solving this problem. Why? Because it helps us to simplify the math. It makes it much easier for us. So that's reciprocity relation. So these four mathematical tools and concepts can be used anywhere or for any material in predicting how that material is deforming. It can solve any problem. So before we round up, let's finally look at the classes of material we have. What are the classes or classification of this material that we can predict? So the first one is called, so classification of materials. I will now explain why. Okay, let's just go on. So classification of materials, we actually have four classes of materials. The first one is called an isotropic material. So what is an isotropic material? An isotropic materials are materials that they have properties that are different in all directions. The properties in every anisotropic material are different in all directions. That's what it simply means. And an isotropic material, in an isotropic material, their stiffness and compliance matrix are fully populated. What we observe in this this compliance matrix, and this is a stiffness matrix. If you observe this, you see that there are zeros. The reason why there are zeros is because we are assuming that this material is not anisotropic. If it were anisotropic, this person that zero will be replaced with elements. You see a value here, a formula here, you see a formula here, and so on. So there will be no zeros for an isotropic material. So I said every time you hear an isotropic material, it means two things. First is that their properties are different in all directions, and another way of explaining it is that the stiffness and compliance matrix are fully populated. There is no zero. So that's an isotropic material. So the second class of material is called orthotropic material. Now what's orthotropic material? Orthotropic materials are materials that have properties that are different in three mutually perpendicular directions. The three mutually perpendicular directions are those 1, 2, 3 coordinate systems that we mentioned earlier. Remember, in orthotropic material, we are saying that the properties are different in only those three mutually perpendicular directions. Only those three. But anisotropic, we are saying that they are different in all 6 directions. Here is just 3. For orthotropic material, we are saying that it's just different in 3 mutually perpendicular directions. So that's the basic difference between both of them. Now for orthotropic material, remember we said in the previous step, we said that we have something we call reciprocity relation. We're trying to say that some of these constants are symmetric. They don't stand alone. So an orthotropic material have 12 constants. If you count each of these constants one by one, you find out that they are up to 12. But because of this reciprocity relation, it has reduced our 12 constants to just 9. So what are they? So for orthotropic material, it has just 9 independent constants. What are the independent constants? We have E1, E2, E3, right? We also have Poisson ratio V12, V13, V23, and finally we have G12, G13, and G23. Do you know why we are writing it Before, if it was 12 actually, what we include there is D21. We also include D31. But because they are symmetric, we are not going to include them. D12 is symmetrical to D21. D13 is symmetrical to D31. So that is why we are neglecting those two. Same thing here. We are going to neglect it. So why we are neglecting it? Because they are symmetrical. So these 9 are the only independent constants for every orthotropic material. So every orthotropic material possesses just 9 independent constants. So let's go to the third class. The third class is called transversely isotropic. Transversely isotropic. So for transversely isotropic, it is a special case of isotropy. What it means is that the fiber direction, what's fiber direction? Direction 1. The fiber direction is unique, but the 2 and 3 directions are identical. They have identical properties. So in transversely isotropic, we are saying that direction 1 is what is unique, but direction 2 and 3 what they have identical properties. So what will happen to our orthotropic material? What will happen to our constant? Our constant will still reduce again. This transversal isotropic is saying that E1, anywhere that have 1 alone, is unique, is standing alone, but direction 2 and 3 have the same property. E1 is standing alone, yes, but what? 2 and 3, they are equal, they have identical properties. So same thing with what? D12 and D13. Why? 2 and 3, they have identical properties. D23 is standing alone. So which other one again? We have G12 and G13. Why? Because they have identical properties. Then G23. Now I'm supposed to include G23 here. Then if you now count, you have how many constants? 1, 2, let me add G23. You have 1, 2, you have 3, 4, 5, and 6. But the thing is, G23 has a particular formula for it. So the formula has made it not to be independent again. What's the formula? Anywhere you see G23, the formula is E2 divided by 2 bracket 1 plus Poisson ratio D23. So with this formula, I can be able to find G23. That makes it not to be independent. So how many independent constants do I now have? 1, 2, 3, 4, 5. So I can rewrite it and say I have E1. Now I can pick any one since they are independent. So since they are equal to each other, I have E1, I have E2, I have which other one? I can pick any one. I can say G13, G23, and G13. So 1, 2, 3, 4, 5. So we have 5 independent constants for a transversal isotropic material. Then the last one is isotropic. So for isotropic material, like the name implies, it simply means that it has identical properties in all the 3 directions. Isotropic materials are materials that have identical properties in all directions. So it means, now I'll go back to my orthotropic material again. It means E1, E2, all the 3 directions, they are the same. I can use E since all of them are the same. The Young modulus in 1 is the same with 2, is the same with 3. So I can put E. The Poisson ratio in 1, 2 is equal to the 1 in 1, 3 is equal to the 1 in 2, 3. So I can just use Poisson ratio B. Same thing with the shear modulus. G12, G13, G23. So how many independent constants do we have now? We have 3. But the truth is also the same way shear modulus had a formula, the same thing applies here. We also have a particular formula for G that makes it not to be independent. So G is E divided by 2 bracket 1 plus Poisson ratio. So it makes it not to be what? Independent. So we have just 2 constants. 2 independent constants. So we've come to the end of this class. At the beginning of this class, we introduced composite materials. We are now looking at how that composite material can deform when you apply stress. And we looked at 4 mathematical tools and concepts that we use to be able to analyze how a material deforms. So in our next video, we'll be focusing on how we can solve problems using these formulas and equations that we have derived here. So we are going to be applying it in our next video. So if you like this video, please do it to subscribe and leave a comment. Thank you very much. See you in our next video.